All right, so the renal system, you may have called before the urinary system. Either way, right, it's the same thing. So we're talking about the kidneys and how they form filtrate, which can be used to produce urine. That's how we're going to get rid of excessive waste and etc. from our body. It does span 2 chapters, as I mentioned just a moment ago. I don't want you to worry about that so much, is that we're really condensing the content that we're going to talk about. The objectives that we're going to focus on in chapter 18 is we're going to look at some primary functions of the kidneys. So it tells us the kidneys do more than one thing. We're going to look at a few things the kidneys do. We're going to talk about the anatomy of the kidneys and then turn our attention more to the nephrons, which are the functioning component of the kidneys. And then we're going to review the phases of urine formation, which you introduced in the last lab that we had this semester. Okay, so that's what we're going to focus on here in chapter 18. If we look at some functions of the kidneys, the go-to answer, right, if I were to poll you before we started this class, I'd say, well, what's the teleological mechanism behind the kidneys? And what would you guys say? Our kidneys what? Filter what? Blood. Okay, they filter blood, and that's true. But we can add a bit more detail about some functions of the kidneys. Not only do they filter our blood, but they make sure a lot of other factors in the blood are actually at what? At set point. Very good. Including the ion concentrations in your blood. We now know after 16 weeks of physiology that our ions better be in set point. Sodium, potassium, calcium, chloride ion, etc. And so your kidneys can help work to ensure ion concentration is at set point. Furthermore, it can also regulate the volume of your blood plasma, eliminating excessive water or retaining water, for example, when water is low, right, or in your dehydrated state, right? Your kidneys can regulate your water volume. Okay, so your ions, concentration, your blood, water. When we mess with those two things, we actually influence the what? The pH. And so now we see here a second system which can regulate our blood pH. What other system regulates our blood pH? The respiratory system, by regulating the amount of carbon dioxide in the body. Very good. It can also regulate, when we change the volume of water, we can change the concentration of water, so the osmolarity of the blood plasma can be influenced by targeting the kidneys. And probably what you're most familiar with the kidneys is their ability to get rid of actual waste products, okay, like urea, for example. So the kidneys are extremely important for us, not only just getting rid of waste, but making sure our water, our ion concentration, water volume, pH, and etc. are at set points. If we turn our attention to the anatomy of the urinary or renal system, most notably there's going to be the kidneys. Okay, how many kidneys do we have? We have 2. Okay, right? Average design would be 2 kidneys. We have one on the left side and the right side. If you look at the arrangement of them, although they look maybe symmetrical, they aren't parallel, directly mirror parallel with one another. Okay, so the left kidney is a little bit higher than the right, but they still function the same and about the same rate of one another as well. The kidneys are going to produce filtrate and also what? What can the filtrate be converted to? Once it's not filtrate, we can call it urine, which is going to be transferred to the bladder by way of these structures called the ureters. The ureters just transport urine from the kidneys to where? To the bladder. What does the bladder do? It stores urine. And then also allows for the removal of it. We can store it and remove it, but we need to call into order the other organ called the urethra, which is the actual physical passageway for removal of urine. So again, your renal system, you can say renal system, urinary system, whatever you're comfortable with. It's comprised of the kidneys, the ureters, the bladder, and the urethra. What type of muscle is surrounding your bladder? What? That's going into anatomy. I don't remember, but what type of muscles are they? They're anatomically smooth muscles. What are they called? That's buried way back up in here. I don't even remember that. Very good. You've had anatomy recently? Very good. And those are smooth muscles, which we can control autonomically. And then, if you recall, the smooth muscles can stretch and expand and hold contents like urine until it's time to go and get rid of it. All right, so that's some basic anatomy of the entire renal system. We're going to turn our attention to a single kidney and look at its anatomy. And before I forget, I have the sign-in sheet going around. Any graded work may be in here as well. And I want you to double check your grade on the most recent handout, number 11, D2L. I was without a computer for a couple of days. I was handwriting and then transferring into a computer. And so I just want to make sure that your grade is correct. So verify on handout number 11, that what you received back is what is a D2L. Urethra. If we turn our attention to a given kidney, it's often described as being bean-shaped. If you look at beans that you could eat, they have this kind of similar appearance. They're obviously going to be much larger than any bean that you may eat, but they're guesstimated to be about the size of your closed fist, right? So if you make a fist, you can guesstimate the size of your kidneys. Anatomically, right, these organs are suspended in your abdominal cavity, and they have an outer connective tissue around it, which is called a capsule. So it's encapsulated with connective tissue, which isn't really shown here, just kind of this, just the colored. It isn't colored, it's actually kind of papery white, the connective tissue on the outside. So that physically connects it, encases it. And then anatomically, the outer portion of the kidney is called the cortex. We've seen these words before, cortex and medulla. We're going to use them here. And that's why I gave you caution at the beginning of the semester. When you say cortex or medulla, I want you to precede it with what organ you're in. So if I were talking about the cerebral cortex, the medulla oblongata, the adrenal cortex, the adrenal medulla. Here I would say the what? Renal cortex. So I'm talking about the kidney, the outer portion of the kidney. And then we would also have the what? We have the cortex and probably the renal medulla. Very good. The cortex looks in this left image, it's kind of lighter area where you can see some blood vessels entering and exiting. If you look at the enlargement, the renal cortex is going to be the area where you're going to find the Bowman's capsule and the glomerular capillaries, and the convoluted tubules is where you're going to find located in the cortex. Underneath that would be the renal medulla. The medulla is in the middle, and it's arranged in pyramids. They're these triangular shaped structures. Can you see the pyramids? Kind of these areas are in the medulla. Portions of your nephrons also extend into the renal medulla, and that's where you're going to find the limbs of the loop of Henle. The descending and the ascending limbs of the loop of Henle will be compartmentalized to the adrenal medulla. So the outer cortex, the inner medulla. What questions do you have about those two areas before we look at another area of the kidney? Even more deep into the tissue is called the renal pelvis. It's highlighted yellow here. In your body, it wouldn't be yellow though. Okay, it's actually kind of white, connective tissue-y as well. It's called the renal pelvis, this kind of fan-shaped looking structure. If we look more closely at the renal pelvis, what do you think the renal pelvis does? It fills with urine, which is being collected from the, it's going to connect to them, but it's receiving from the collecting ducts of multiple nephrons. Okay. So the renal pelvis collects, we can actually use the word, we can use the word urine here. It collects urine from the various collecting ducts. So it's kind of like a little sieve. Everything's kind of just filtering. I want to pull that word back, just collecting down here in the renal pelvis. So it's like a funnel maybe is a better word to use. And so the renal pelvis will then funnel urine, then it can go into the ureter. So it collects from the collecting ducts and transfers urine down to the ureters, or transfer down into the bladder. You can also see in this image a very nice supply of blood. So our kidneys have to receive a constant supply of blood because our kidney's job is to filter the blood. Ion concentration, water volume, etc. At set point. Okay. What questions do you have about this kind of, we call gross anatomy before we look at a single nephron? Uncomfortable? Cortex, medulla, pelvis? We're now going to turn our attention to these microscopic structures called nephrons. They're tiny, but they're well developed to do what they do, which is to filter. So if you want to understand how the kidney functions, you really need to look at how individual nephron functions. And within a given kidney is proposed to be upwards of 1 million nephrons in each kidney. So if you've got 2 kidneys, you have upwards of 2 million nephrons filtering your blood continuously. So let's look at our nephron. I want to always point out that when you look at images of a nephron, it's just someone's interpretation of how this little convoluted tiny microscopic structure looks. And so you can't look at all, you can't go do a Google search for nephron and assume that they're all drawn exactly the same, because everybody's going to draw something exactly the same. Okay, so where I'm leading you is it's a complex structure, so you really need to find some landmarks and kind of work through it like a maze, so you can understand physically where you're at. Because if you're at a different location, that part is going to do a different one. Function. Okay, so the anatomy and physiology relationship is certainly applicable here, like we've been applying all semester. And so we're also going to study, coming up, and you saw in your handouts, that a nephron is going to be this relationship between tubes and blood vessels. In this image, the bulk of the blood vessels have been omitted, so we can study just the tubes. So we're going to turn our attention to the tubular component of a nephron. And also, just to give you a bit of caution, this thing looks like a plastic tube or something. But this is made up of cells. They each have their own membranes, each have their own nucleus, they express their own receptors, right? Each maintain their own set point. But it's just oversimplified into this entire structure. So if you look at the tubular component, there's really, I think, 2 landing marks that you can go to help find out where you're at. The 2 that I think are the most useful is one, just find a collecting duct. If you find the collecting duct, you know which part is going to dump into this. What part drains into the collecting duct? The distal convoluted tubule. Okay, and then you could work backwards, right? Me, it's hard for me to go backwards, and so it's easier for me to land at the Bowman's capsule. So if you find the Bowman's capsule, you can find where filtrate is first captured. Okay. So let's label this. We have surrounding our glomerulus is the what? Bowman's capsule. You can call it the Bowman's capsule, or you can call it the glomerular capsule. Okay. Either way is acceptable. Okay. The capsule, what does the word capsule mean? Encompasses. surrounds. The capsule surrounds what? The glomerulus, which is a set of what? Capillaries. Very good. So let's go ahead and label the glomerular capillaries. Notice I gave a couple of alternative names. I could say the glomerulus, or I could say what they are, glomerular capillaries. The glomerulus is the what? The glomerulus is, just repeat what you said. Capillaries. The capillaries are surrounded by a capsule, okay? So around tube. So don't confuse the capillaries from the thing that's surrounding the capillaries. The glomerulus is surrounded by the Bowman's capsule. It's going to trap what? What does the glomerulus trap? Filtrate. So we'll come back when we get to the blood vessels how that's actually formed. Okay, very good. But once filtrate is trapped, it's pushed through the tubes. What is the next structure of tubes called? Proximal. You can call it proximal tubule, or you can call it proximal convoluted tubule. It's convoluted because, what does that mean? It's folded. Why do we want this tube to fold? To increase surface area. Check in your work from your handout. What happens at the proximal convoluted tubule? Very good. We see a lot of reabsorption of filtrate, and it goes in the interstitial fluid, and it may even probably going to go back into one of those peritubular capillaries as well. So we have a lot of surface area to ensure a lot of reabsorption. And just to help you out, to understand the kidneys, you really have to understand what we studied in chapter 14 about blood vessel mechanics and how they work. And so we're using those exact same terms about absorption and filtration here. So let's just recap. Filtrate is formed at the glomerulus. It's trapped by the Bowman's capsule and then pushed down its what? What can push it? Very good. A pressure gradient. So high pressure is pushing this filtrate through the tubes. It goes through the proximal convoluted tubule where a lot is being what? A lot of the filtrate is being reabsorbed. Anything that's not reabsorbed stays in the tube and then would enter in what's called the what? Descending limb of the loop of Henle. What happens at the descending limb of the loop of Henle? Water reabsorption. Check your work on your handout. Water reabsorption. Tying that back into chapter 6, which hormone can increase this water reabsorption? Good job. Anti-diuretic hormone can target the descending limb of loop of Henle to enhance water reabsorption. You guys are obviously on it, so I'm going to push you a little more. Where does anti-diuretic hormone come from? Posterior pituitary. There is a hormone from the adrenal cortex that influences the kidneys. We'll get there in just a second. Very good. So anti-diuretic hormone from the posterior pituitary can also target the descending limb of the loop of Henle to promote what? What are we promoting? Water reabsorption. Filtrate is then pushed to the ascending limb of the loop of Henle, where it becomes more permeable to sodium, potassium, other solutes. So which hormone from the adrenal cortex can target the ascending line lobe of Henle? Aldosterone. Aldosterone can target the ascending line lobe of Henle. Promote sodium reabsorption. Filtrate then pushes to the what? What's the next region? The distal convoluted tubule. Distal referring to more far away. Okay, we're more far away from the glomerulus. What's happening at the distal convoluted tubule? You're still going to see some reabsorption. Could be lipid soluble molecules. What else could be reabsorbed here? Probably could reabsorb some more water. Yes. And even more, like we just listed. What else could we reabsorb? Some more, like solutes, like sodium, for example, may happen. But we begin to see a higher proportion of what's happening here at the distal convoluted tubule. See a lot. Still seeing reabsorption, but here we begin to see a high proportion of what? It's going to be, the bulk of it is going to be regulated. If you're looking at charged particles or even water, for example, things that aren't regulated are going to be the more lipid-soluble substances. So both can still occur, so you're correct. Or maybe give me an example of something we haven't talked about, maybe. You can think of one, Levi. So sodium chloride. Is there anything that you're thinking of, that Levi, that we haven't mentioned, a solute? So urea was mentioned, but urea, I'm going to come back to urea for just a second. Where I'm going is not only can we reabsorb, but what else can happen here? See secretion taking place. There's going to be a higher proportion of secretion happening along this distal convoluted tubule end. And byproducts such as urea can be secreted or even reabsorbed because they are lipid soluble products. They're lipid soluble. What can we do with them? We can actually. We can reabsorb lipid soluble. So what can we not do with them? We can't store them. And so they're always exposed to their what? Gradient. So they're going to diffuse at 50% to reach what? I'm going to change the word. I'm going to go ahead and use the word equilibrium. So even though urea is a waste byproduct, it's lipid soluble. So if it's a waste, you think you should get rid of it at like 100%, right? But through each filtration, you can't. You can only get rid of it about how much? About 50%. Because some of it's secreted, but the balance of it is reabsorbed. Even though it's not necessary, it's reabsorbed because it's what? Lipid soluble. Same thing goes for, say, your estrogens, progesterones, testosterones. Even though your body makes them, 50% by the time it goes to kidneys are going to be where? Located in your what? In your urine. Everybody's like a dirty word, like, I can't say that. It's not a dirty word. Well, if you guys look at your microscope, it may be depending on what was in your sample, but it's not the word urine is not a dirty word. But this makes sense, right? If you go for a pregnancy test, what's the easiest way to test for it? Urine test, and test for the presence of specific hormones and concentrations in them. Because they're lipid soluble, you can just pass them in the urine. Very good. So secretion, the proportion of secretion begins to increase over the distal convoluted tubule side. However, secretion can happen where? Moving substances back can happen where? Not only at the distal convoluted tubule, but probably. Where else do you think you could secrete products into the filtrate? Where else could solutes be secreted? At the tubes, besides the distal convoluted tubule. Do what? Did you say collecting?
Yeah.
Sure, we can secrete at the collecting duct. Where else could we secrete? Into the proximal convoluted tubule. The point of that is, even though in the beginning portions of the nephron we see a high proportion of reabsorption, there may be secretion, especially if products are lipid soluble. They can just diffuse down their little concentration gradient. But it's the proximal convoluted tubule where we see most of our reabsorption taking place, but not all of it. And certainly some secretion can take place there. It looks like we're going to get into the vascular component in just a second. So before we move on to the rest of the nephron, what questions do you have about the tubes of the nephron, their location and or function? What is pushing the filtrate through? We have to have a pressure gradient pushing it through. So the pressure is going to be highest where? At the capillaries and least at the ducts. Because we're going to push it down at the collecting ducts. I was going to say something, but I missed it. Not all nephrons are built exactly the same. They'll all have these features which we identified, but some have longer loops and some have shorter loops. The nephrons which have the shorter loops are called cortical because they are closer to the what? Cortex. And by contrast, some are much longer and they're called juxtamedullary. Juxta, what does that mean? Go to juxtaposition, so it's, is it opposing? It's not opposing, it's right, what? Juxta means next to, right? So the juxtamedullary area next to the medulla, renal medulla. Juxtamedullary nephrons next to the medulla, they're actually looped down more deep into the medulla of the kidney. So the juxtamedullary nephrons have much longer loops when contrasted to the cortical nephrons. The question is then, well, why? Why the difference? And the reason is that the longer nephrons extend into the medulla, they help establish a concentration gradient in the interstitial fluid. So the more deep you get into the medulla, the more concentrated the interstitial fluid is. And it's the juxtamedullary nephrons which contribute to this. So again, the juxtamedullary help establish a concentration gradient from the cortical to the medulla region of the nephron, or excuse me, of the kidney itself. To quantitate that, some average numbers from the cortex region, the concentration may be like, say, 300 milliosmoles out in the interstitial fluid. And the more deep you get into the medulla, it may be like 1,200 milliosmoles, so 4 times concentrated in solutes than when compared to just a little bit higher up the nephron. Okay, so we have a nice concentration gradient. Why do we want a gradient? To move things. Do what? To move things and help. It does aid in the concentration. When we move solutes, it influences the concentration of the filtrate, which influences the concentration of the urine. So again, the difference is that the juxtamedullary nephrons just help establish a concentration gradient. So we can move solutes, so we can change the concentration of the urine. Which makes sense, right? If you were to go to the bathroom now versus after you drink a liter of water, you'll know that the concentration of your urine output is going to be variable. And so that's how we can help create these changes, using this, establishing this concentration gradient in the medulla.
So why the difference? Is it just because it's fan shaped and there's not room for all of them to descend all the way down?
Why the difference is we just don't need the sheer numbers of the juxtamedullary ones.
What is it, like 50-50 of each?
I don't know the ratio. Your book may actually give the ratio. Quantitatively, though, there would be more of the cortical than the juxtamedullary, but I don't know what the proportion actually is. Does anybody know? The 80? Okay. I don't remember the proportion, but I don't think it's necessarily a room thing. It's just not necessary. So a few nephrons are necessary to keep the gradient, and the rest use it, basically. Very good. Additional questions? And Levi will look that number up for us. It looks like a reference. All right, so I want to turn our attention now to the vascular component of the nephron. We know that we have to have a good blood supply to the each nephron. What is it?
The juxtamedullary compromise 15 to 20%, so 80%.
So about 85%, 80 to 85% of your nephrons are the cortical ones, and then the balance are the juxtamedullary. Thank you very much. In order to form the filtrate, we have to have a blood supply to each nephron. And half of you guys got to have lab with me, half of you didn't. So I tried to really iterate if you were in the lab with me, in that the nephron anatomy is unique, in that we have an arterial, then a capillary, and then instead of draining right into a venule, we have another arterial, and then a whole other set of capillaries. So it's kind of unique in that there's 2 capillary beds in each nephron and 2 sets of arterioles in each nephron. Any other organ in the body wouldn't have this setup, which is good because your kidneys are designed to filter the blood and make urine. The rest of your body is not designed to do so. So that's why we have to call in these extra anatomical structures. So we're going to use these terms which we've seen before, afferent and efferent. Again, I just enunciate so we're clear on what I'm talking about. So afferent means what? Towards. Efferent is away from. And so the afferent arteriole carries blood to the glomerulus. The glomerulus is just a set of capillaries. Their job is to filter, to form, at this point, we just form what? We filter to form filtrate. We don't want to use the word urine yet, because what are we going to do with the bulk of everything that's filtered? We're going to reabsorb. So we don't want to call it urine yet. Once we're done processing it, then we can call it urine. So the glomerulus filters to form our filtrate. But these capillaries are really cool. They filter only, they don't reabsorb. And that's what makes the kidney, the nephron, do its thing. We have capillaries that don't exhibit bulk flow. They just have filtration only. No reabsorption.
So the glomerulus
they don't work is when you see renal failure. And they're reabsorbing, you're not forming filtrate, and it's not good.
What would cause them to fail?
So many reasons why someone might have kidney failure: high blood pressure, diabetes, cancer, physical injury, all kinds of, just lots of kidney stones, backing up the pressure, etc. Because so our kidneys are super, super, super important, and we need a constant blood flow to them so that we don't mess up the mechanics of these capillaries. So if I want to filter only, I need to make sure what is super high. The pressure. The pressure has to be even higher in these capillaries than any other capillary bed in your body. Because if it was very minimal, these capillaries would reabsorb. We don't want them to reabsorb, we want them only to filter. So the pressure has to be super duper high and that's a physiology term, go with it, right? It would be super duper high to make sure that only filtration happens and no what? Reabsorption or absorption takes place. The way that your body ensures that there is only filtration is to throw in this extra arteriole. What is the extra arteriole called? The efferent arteriole. Okay. Let's turn your attention and look at the diameter of the lumen of the arterioles. What do you see there? Which one? The efferent arteriole is smaller in diameter than the afferent. If we decrease the radius, we increase what? Resistance, which decreases our flow, and that's going to cause a backward pressure increase. So the reason because the capillaries are in the middle, right? So you're trying to blast blood in, and it can't get out very fast, so it's forced. Right? Some of it's going to be forced out through the capillaries to filter. But some of it certainly can exit via the efferent arteriole. So that's another thing that you can look at if you're trying to figure out blood flow. The afferent arteriole is probably a little bit larger in diameter than in the efferent arteriole. That relationship creates a what? Pressure gradient to ensure that these capillaries don't reabsorb. They only filter your blood plasma.
So does the efferent, does it constrict based upon if it's not enough pressure?
The efferent arteriole can, but any constriction and dilation is going to happen, I don't say any, the bulk of the constriction and dilation is going to happen at the afferent arteriole. Okay, and that's actually where I'm headed right now. And so what I want to do is turn your attention to this. If you look at this right here, where my hand is, the smooth musculature of the afferent arteriole, notice it's a little bit thicker when compared to the efferent arteriole. That tells us we have a more motor control at the afferent end than we do at the efferent end. And so that does mean that the afferent arteriole can constrict more forcefully and quickly when contrasted to the efferent side. Okay? But your kidneys are so important that we have to control the blood through them, not only just precisely, but every millisecond. Your kidneys need to monitor, your nephrons need to monitor the blood flow through them. And so we need something faster to monitor this than your nervous system. What could give us faster control than your nervous system? If I want to control an organ, if I want to control it fast, faster than the nervous system, which is already pretty fast, really fast. We're going to give it some type of intrinsic control. You said the adrenal medulla is going to produce hormones from the nervous system, and so that it can affect it extrinsically, which is going to take longer than a form of just intrinsic control. So our kidneys can be intrinsically regulated. And it's these cells surrounding the afferent arteriole. What happens when the blood flow becomes elevated? What's going to happen to a blood vessel if we just all of a sudden bring a bunch of blood in there? What's that blood vessel going to do? It's going to stretch. We have mechanoreceptors that feel the stretch, that detect the stretch. So if your arteriole has a set diameter and it stretches, what do you think the muscles might be told to do? Constrict. And so in this purple region, this whole smooth muscle and these granular cells provide a source of what kind of control? A source of intrinsic control. It's going to be the smooth muscles, and also these granular cells can have some mechanosensing. So if the blood pressure gets too high, these will detect that pressure and then respond by doing what? Constricting. To maintain what? To maintain homeostasis, to maintain set point in diameter, set point in blood flow. When my blood flow is too low, say my blood pressure drops for some reason, and my blood flow to my nephron decreases, can the kidney respond intrinsically? It can. The muscles would probably have to relax to bring that diameter back to set point. Okay, so it's just precisely just micromanaging that diameter to make sure the blood flow is constant to the kidneys, because you need to constantly filter your blood. Can the kidneys be extrinsically controlled? Yes, they can, and we'll turn to that in just a second. Very good. So let's just review. The afferent arterial diameter is what when compared to the efferent? Larger, so that we can establish a good pressure gradient to ensure that the glomerular capillaries filter, form only the filtrate, but do not reabsorb. Furthermore, we just added that the kidney can intrinsically, each nephron can intrinsically regulate it based upon stretch. Intrinsically just determine the amount of stretch or relaxation to ensure constant, adequate blood flow, right, to that nephron, so we don't foul up that pressure gradient, so we don't stop filtering at the kidneys. All of these cells working together comprise the juxta glomerular apparatus. And so if you work through the term slowly, just apparatus, okay, a thing, a device. Where? Juxta, we said, next to, adjacent to the glomerulus. Okay? So these happen to be next to the glomerulus. Okay? So these are these sensing cells. They also have another function of renin production. These granular cells, the purple ones, produce renin, R-E-N-I-N. These cells also produce renin, R-E-N-I-N. We're going to talk, it's in your guided notes to discuss, but I'm not sure that we'll have time to talk about it today, so you may kind of get a free pass on that hormone pathway, but we'll see. That is, wow. All right, so let's look at the rest of the blood vessels to the kidneys. We said we have arterial supply. The one that takes blood to the glomerulus is the afferent. That establishes a nice pressure gradient so that we can filter at the glomerulus. Blood can then exit via the efferent arteriole and then drain into the blood would go into the blood is in your what? Vessels. So what vessels do we see next? The paratubular capillary. The blood, if it's in your vessels and it didn't get filtered, it's not going, probably not going in back into the tubes. It may be if something is secreted, but it's just not, it's not going to just hop, like magically hop in there. So it's going to continue through, right, the vasculature network. So let's just recap. At a nephron, we have our afferent arterial supply, where blood can be filtered at the glomerulus. If it's not filtered, it exits via the what? Efferent arterial, then it enters into our network of what? Peritubular capillaries. These are the capillaries where? Peri, around, surrounding the tube. It's these capillaries that can reabsorb from the proximal tubule, that can reabsorb from the descending limb, that can reabsorb from the ascending limb, that can reabsorb from the distal convoluted tubule. Okay. They can also do what? They can not only reabsorb, they can also secrete products back into the tubes. Depending on if it's controlled transport using a transporter or something just lipid soluble, just diffuses down its concentration gradient. And I think it's important to, at this point, so we've been using the terms to differentiate filtration versus secretion. Because fundamentally they sound the same, right? You're moving something from the interstitial fluid or maybe the plasma into the tube. So filtration occurs only where? At some type of capillary. Capillaries filter. Okay? Secretion of a product, if it's secreted, it may come from the blood plasma, but it also may come from the interstitial fluid, or it may come from one of the cells making up the tubes. And so secretion doesn't imply that a capillary actually filtered it. Maybe just something in the interstitial fluid being transported across the tube cells and back into the tubes. And so it may be very specific. Like if I specifically want to secrete, say, potassium, it's physically being transported using a potassium transporter, for example. So it doesn't have to happen at a capillary. It may be coming just from the interstitial fluid. And maybe a better way to differentiate that, filtration is formed by using a what? To filter something, I need not only a capillary, but also a what? What kind? Pressure gradient. Whereas secretion is probably not going to use a pressure gradient, but more a concentration gradient or some mode of transporter and or a transporter. What questions do you have about differentiate pressure filtration versus concentration secretion? I want to go ahead and differentiate some terminology. I think we kind of implied this through our discussion so far. There's a difference in the terms between blood plasma versus interstitial fluid versus filtrate. Your blood plasma is located where? In your blood vessels. Okay, very good. Interstitial fluid is located. So between cells, outside of the cells, outside of the blood vessels. So it's that fluid between cells. It's not trapped in a blood vessel. It's not in the cell. It's between the cells. In the term filtrate, where is this located? Your filtrate, let's be more specific. What? It's formed at the glomerular capillary. So where would it be located then? Trapped by the Bowman's capsule, transported through. So your filtrate is located in your, you can include the entire nephron. All the renal tubes, the Bowman's, so you can be more inclusive than just saying the Bowman's capsule. That's where it's first trapped. In the tubes of the nephron. Because the nephron includes the vessels as well. So I'd be more specific, the tubes. And even in the collecting duct. The filtrate is just the fluid that's flowing through all the tubular structures. So you're having a constant exchange, right? Blood plasma will be filtered to form our filtrate. Anything that's a filtrate can be reabsorbed back into the interstitial fluid and even reabsorbed back into your blood plasma, which then could secrete something back interstitial fluid and back into your filtrate. I really could add a fourth term on here. What fourth term could we differentiate here? What fourth fluid term could we differentiate here? Blood plasma, interstitial fluid, filtrate. What else could we add here? I think we could add urine. I would add the word urine here, the fluid urine. Urine is located where? First in the renal pelvis, ureters, bladder, urethra, city wastewater. But not in the pool. So let's review, and you can check your work for how the events that happen in order to form urine. And you can check the very last page of your guided notes. In order to form urine, what first has to happen? The first process is filtration. Filtration happens where? At the glomerulus, or you could say the glomerular capillaries. So the first process is filtration. We use a what? Pressure gradients established by the relationship between the afferent and the efferent arteriole. Right, filtrate is pushed out. If blood plasma isn't filtered, it stays in the capillaries. It can be involved with reabsorption and secretion as well. So once filtrate is produced, we can then reabsorb selected products back into the peritubular capillaries. What might you need to reabsorb? What kind of water, solutes, nutrients, hormones, anything that is lipid useful and maybe even just not useful and lipid soluble. So anything's exposed to that pressure gradient or concentration gradient. If it's lipid soluble, it could be reabsorbed. But really, we're trying to pick up glucose, sodium, potassium, hydrogen ions, water, the things that your body does need. Anything that's excessive or maybe lipid soluble could become secreted back into the what? You guys are all okay with those terms, right? So we said interstitial fluid, and then you could say the tubes. Okay, so if it's being secreted, it's going back into the tubes. Once this modification, reabsorption secretion is done, once the filtrate travels through the collecting duct, we can call it what? Urine. And then at some point, you're going to excrete it. Physically eliminate it from your body is a process of excretion. What I want to do now is show an oversimplified animation of these processes. It's certainly not, it's far from 100% correct, and it also doesn't illustrate capillaries, but I think the processes will help you. While I'm thinking about it, the interactive physiology videos that I had you guys look to, there were some issues about the Adobe Flash player. Were you able to get it shown? Not it. There's been difficulties on, I think, were you using Safari? Okay. There's been difficulties on Safari. I've had some people not be able to get it and some people able to show. But if you go in the study area, Mastering A&P, go to Interactive Physiology, and there's 3 or 4 videos for the urine formation. I would go there. They give you heads up in the last lab to watch those. But if you have trouble, you have to do something with the add-ins.
It works on Internet Explorer, that's the only one that usually got.
So if you still have Internet Explorer, I think Firefox, it works fine as well. Not sure about Chrome, but it's the extensions. It won't work on Chrome. Okay. So Internet Explorer, Firefox, I'm pretty sure, but it has something to do with the Java settings, which I'm not up and up on. So just check that. So if you've had trouble using an Apple device, you might want to try and use a non-Apple Windows device to do that. So this animation I'm showing is not from the study area. It's a different one. All right, so I'm going to go ahead and turn to the kidney function. This image tries to reiterate what I mentioned about the juxtamedullary nephrons and how the concentration of the interstitial fluid is less concentrated in solutes in the cortical region and becomes more concentrated in the more deep you get into the medulla, just implied by the gradient that we see there in the coloration. Right? So it's more concentrated in solutes, more in the medulla than it is in the cortical region. If we look at this oversimplified nephron, this kind of, what is this area where my arrow is? Bowman's capsule, then it extends into the proximal convoluted tubule, then to the descending limb of Lupin-Henle, then the ascending limb, then we get to the distal convoluted tubule, and now the collecting duct. If you look at the legend on the far left, things that we're going to see include ATP, salts like sodium, potassium, whatever, shown in red, water shown in white, nutrients like glucose, amino acids, and things that your body needs to use, shown in green, and then waste products like urea, for example, shown in blue. The first process shown here is what? Filtration, high pressure established by, right, where's my arrow at? Afferent arteriole, and then over here, the arrow really should go way over here for the glomerulus, okay, but the smaller diameter arteriole is the efferent arteriole. So you can see products being filtered out. Reminding you, capillary anatomy, anything that's not big enough, or assuming that it's too big to fit through those pores, it's not going to get filtered. So you wouldn't find like your large red blood cells or even giant proteins like albumin. They're too big to filter out, and so they're going to stay in your capillaries and be moved along with the fluid. But we're pushing out small products that can fit through the pores, and lipid-soluble products, hormones, and etc. can be filtered out through the capillaries. As soon as filtrate is formed, along the proximal convoluted tubule, we see some selective transport of particles. So glucose, we've talked about glucose. Every biology class you talk about, you're going to talk about glucose. We know that it's important and invaluable. You never know when your next meal is. So it doesn't make any sense for your body to filter out good glucose if you're in a starved state, right? So we need to reabsorb those nutrients. So right off the bat, we reabsorb glucose, some water, salt, sodium, etc. can be reabsorbed. As the filtrate travels through the tubes, we can see more reabsorption of solutes. Shown here is primary active transport, but definitely secondary active transport is really important for how the kidney tubules reabsorb useful substances. Okay, but we're just picking off the good stuff. Pressure is pushing the filtrate down, and then we'll get to the which? This is the descending limb of the Lupin-Henle, where we said it's really permeable to water. And then pressure pushes it where it becomes more permeable to salts. And then it pushes through where we can still see some more reabsorption. And then we get to the distal convoluted tubule, where we're shown is what process. Not only do we have reabsorption, but we also have secretion happening. They could have just as well shown secretion a little bit along at the proximal tubule, but they just chose not to.